Hi, so today I'll be trying hopefully the fourth and fifth problem of the division, starters 82 division 2 contest of Codechef. This is find EX. Chef has four positive integers A, B, C, and D such that A mod B equals C mod D. Okay. Okay. Find the smallest positive integer x such that A plus x mod B equals C plus x mod D still holds. It's guaranteed that such an x always exists. This line contains a single number of test cases. 10 to the 5 test cases, and you can have these guys' sizes are to 10 to the 9. Okay, let's look at some examples. Four, 7, 4, 8. I guess it's non-zero. You need to give x. Smallest positive integer x such that this holds. I see. 1 makes sense. And 5, 8. Okay. 5, 1, 8, 2. Yes, 2, 3, 2, 4, 3. It's 0 or 1, right? So fine. I see. Interesting. Now, one obvious upper bound to this is um LCM of B and D, right? Um, if you add this, this definitely works. Okay. But that's only okay. So you need A plus X mod B to be equal to C plus X mod D, but you don't need A plus X mod B to be equal to A mod B, which is like an extra sort of um property I get for free if I use LCM of B comma D, but I totally don't need that. Um, okay, so I will give myself 30 minutes before I look at the editorial, right? Yeah. It feels like there's some structure I need to exploit. Maybe first of all, just take the mod. Like, don't leave it like this. That's kind of annoying. So I have 3, 2. So just write it as 1 mod 2. And I have 4, 3. Um, oh, it's going to be the same. We've been promised it's the same, right? 1 mod 3. So yeah, that is a like to see those numbers are a bit annoying. So this I would write as um, 0 mod 1 and 0 mod 2, right? And now you're asking me the smallest such that they continue. Now you realize that there's actually a nicer upper bound. It is, oh no, do, is it all right to claim it's B plus D? I'm not sure. Why do I claim that you should get it within B plus D? Or that's not true maybe. Okay. Now you're asking if you add 1, get 0 mod 2, 3, you add 1, 1 mod 2, 1. So let it currently be X. So after the first round, this repeats after D minus X. This repeats to B minus X, and the next round onwards, this repeats after D. This repeats after B. Mhm. What is Chinese remainder theorem again? What does it give you? Hmm. I think what it does is what this Chinese remainder theorem does is given um, A mod X and B mod Y, it gives you C, which is equal to A mod X and is equal to B mod Y, right? If X comma Y are coprime. Does Chinese remainder theorem give you the smallest? I don't know that it gives you the smallest, and I'm not 100% sure that this is correct. If it does, this is just a special case where I need to find the C. Because I'm dealing with in the mod X. Am I in the mod XY world? How would I know if I'm in the mod XY world? Um, I am, because after every XY steps, um, I see a repeat, right? Yeah, I'm in the mod XY world. So then does it give me, if it gives me the smallest, then I just need to do Chinese remainder theorem with AX, AY, if this is truly this Chinese remainder theorem. Oh, I need to check this. If X and Y are coprime. Else, if they're not, because they don't give me any such guarantees. Currently, they're the same. So assume both of them started at 0. You're literally doing 0, let's say 4 and 7. 2, 3, 4, 0. 2, 1, 2, 3, 0, 1, 2, 2. What? Interesting. What? Is this even right? 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 6. 0, 1, 2, 3, 4, 5, 6, 0. That's crazy. So if they'd given me 3, 4 and 3, 7, I'd have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25. Crazy. Did it not match even once? No, 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 no. So the answer for this is 25. Hmm. And it says all solutions are congruent, so that's fine. So you just pick the smallest one. Mm. Mm. Now assume I have this Chinese remainder theorem, which will this given A, B, C, D give me some X which is congruent to A mod B and which is congruent to C mod D. What do I give this such that it spits out this X? Is it okay to, can I just ask it for plus one? So in this case, 0 mod 4 and 0 mod 7. And then it'll give me something that's congruent to this. And that is 25 in this case. But now the question is, why is that okay? Would Is it possible that doing plus two sometimes gives you the better answer? In this case, not. And in all the examples I saw, that's not true. Hmm. Would plus one. Oh, wait, I'm thinking something wrong. I mean, thinking a lot of things wrong. Hmm. To add the same number. So is this a fair algorithm? I mean, it's not fast or anything, but to say, mm, suppose 3, right? And then just 3 mod 4 and 3 mod 7. You like make it 0. And then you'll get 28 minus 325. And then you ask 1 mod 4 mod 7. Then you'll get 1, which is 29. 29 minus 326. Hmm. Oh, is it? That's it. If I start at 0 to get 0 again, I need to do add LCM, and then I take away the number that's already there. If it's that's it, I'm going to. Why does that make sense? If you start at 0, the only time you'll get 0 again is if you do the LCM, right? And that's the fastest thing to reach, right? That makes sense. So is it just LCM minus the number, which is crazy? And you don't need all of this Chinese remainder theorem and all. Okay, why would it be LCM minus the number? Um, Okay, let me write this claim. Given A, B, C, D, reduce, let's call it to X, B, X, D. Solution is LCM B, D minus X. Reason. Yeah. 0. Okay, I'm not writing the reason. I don't know how to say it properly in words, but 0 is the closest number to reach. Yeah. Should be, that's it. Okay. Okay, maybe I should try stating it in words before looking at the editorial. Okay, why do I make this claim? So you need to find the least number before it's equal again. The claim is, okay, first of all, claim lowest number it is equal again is 0. Because if it is some, oh wait, no, that's not true. Okay, if X is not equal to 0, lowest, oh wait, this is also not true. Because if it's like just 3 more 7 and 5 or 7, obviously the next best is, sorry, 3 more 5. The next best is just adding 1, right? 4 more 7, 4 more 5. And that is definitely not LCM of B, D minus X. So are there like cases to this? Um, okay. Okay, so first is if doing +1 is less than equal to B, and I mean less than B, not equal to, very specifically not equal to, and less than D, then return 1. Else this LCM of B, D minus X. So the claim is, in this case, claim 0 is the first time they are equal again. And you can prove by contradiction that this is the case, because if you claim that the first time they're equal again is some other number k, just subtract k, and then like k ago you would have gotten 0. So 0 is the first time they're equal again. Now the question is how to get 0. If you start at 0, the first time you'll reach 0 is again is doing by LCM B comma D, right? And what you want to do is LCM B comma D minus x, because you've already done x. So yeah, that should be the solution. That took me long enough. But yeah, let's anyway see the editorial. Yeah, I just went mad with Chinese. But anyway, that was a good revision of what that does. Find x. Okay. First, notice that only remainders matter. Let's replace a with that's true. We only need to solve. Oh, by the way, I can't just do um less than. I should say equal to 0. Equal to b, yeah. I think they did it more clearly. Consider an integer x for which equality holds. Yeah. Yeah, same thing. Okay. Setters code. Wow. Oh, you can just use underscore underscore GCD. Nice. Yeah, I feel weird taking this long for this. Or at least I didn't like. Mm. Oh, this is STD GCD. And what is underscore underscore GCD? Or maybe I can just use GCD. Yeah, yeah, yeah. This looks fine. Let's try one more. Wow, this looks like there's a lot to read. Let's recover from taking an hour to think about LCM. And then an array of segment and an integer m. Interesting. Okay, looks like the question is initially you have an array A, right? And you're given that all AI are less than equal to some m, an integer m. And you're given a permutation P of length n, right? So first you do is replace all zeros. Okay. So then you're given a permutation P. Okay. First you form A prime, which is obtained by A, but replacing all zeros with some positive integers less than or equal to m. Do they all need to be equal? They don't have to be equal. So some equal to m need not be equal. I don't know if, okay. And then in the ith step, you set a prime I to a prime pi. Okay, and a prime is said to be beautiful. If after transformation of n steps, all elements of array A prime are equal. Equal. Find the number of such beautiful arrays A prime, changing the zeros in array A to any value less than equal to m. So is it, so first I guess number of possible A primes, among those we need to find the beautiful one, right? Of possible A primes is how many ever zeros positive integers less than or equal to m. So let z be the number of zeros. So for each of those can have m possibilities, right? So you have m to the z A primes. But how many are beautiful? I guess that's the, let's see. 10 to the 5 test cases, sum of n overall test cases won't exceed this. Okay. Okay, yeah. M is less than 10 to the 9. So the number of beautiful arrays itself are 10 to the 9 to the 0 less than equal. Okay, so first is nm. Let's see. Four, 3, 2, 1, 4, 3. This is the permutation. And 0, 2, 0, 2 can have up to values, right? 1, 2, 3, 1, 2, 3. So for this, there's 9 possible values. Um, replacing all, right? All 0, yeah. So let's just replace it by 1 first. Both of them 1, 2, 1, 2. Then what happens is this gets replaced by 2, so it becomes 2, 2, 1, 2. And this replaced by 1, so 2, 2, 1, 2. This replaced by 4, so 2, 2, 2, 2, 2, 2, 2. So this is beautiful. Nice. I believe any array will be beautiful because first you will go put 2 here and then you'll get 2 back. Put 3 here and then you'll get this back. So all 9 should be beautiful. Yeah. Okay. Okay. Um, 3, 2. So 2 is the max. 3, 1, 2. That's the permutation 0, 0, 0. So obviously if I replace them by 1, 1, 1, that would work. Um, gets whatever 3 has. And then this gets whatever 1 has. This gets whatever 2 has. So I guess same thing, 8 here. I see. Yeah, interesting. Yeah, if it's cyclic like this, if it's peacefully cyclic, hmm, I see. I feel like it's important that in the ith step, only the ith guy changes. It's annoying that there are some guys already present. Oh yeah, okay. What if I always had all zeros? Okay, let's take a simpler version of the problem where um there are, I mean, there's no elements present. Then how would you solve it? It's just all zeros. And Now you're like, for how many arrays will this permutation end up giving you the same number everywhere? Yeah, I think, yeah, like I was saying, I feel like the fact that the on the ith position only the ith guy changes is important, because what does that mean? It means that everyone has to be equal to whatever is in the first element of the permutation, right? Everyone has to be equal to that. So, okay, if, for instance, three, if the permutation was 2143, after whatever is in position 2 comes here, this doesn't change anymore. So that means everything has to be equal to whatever's here. Okay, so I feel that's good progress. Um, Everything has to be. So now, okay, I'm given an empty thing. I'm given all zeros, basically, and I'm asked to solve this. So I'm solving same problem, but all zeros. Okay, so what's in position 2? Let's say some x is in position 2. Now in the next step, this will become x. So step 1. So we'll look at position 2 and look at what's there. Okay, and then step 1, this will become x something something. Step 2, this either has to be 1 or it has to be, if this is 1, we're good. We don't need to worry. If it's something else, that element should be x. So in this case, it's 1, so we're good. So step 2, nothing happens. X, something, something. Right? Step 3, this is 4. So we're forced that this also has to be x. Three had to be x. Wait, what is this telling us? This is telling us like the constraints. If 1 is x, 3 has to be x. Right? Those were the constraints. X. And then these guys can be whatever. So I have m into 3 possibilities. Sorry, what was m? 3, right? Yeah. So 3 into 3 into just 3 possibilities for these two, but that got taken care of. I see. Nice. I feel like I can continue this idea. Okay. So this is so I'm looking at the permutation and thinking, okay, let's see. 3, 1, 2. 3, 1, 2. What am I thinking? Thinking whatever step 1 is fine. If, look, let's say 3 was x, something, something. This must be x, something, x, after step 1. After step 2, this is x, 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 and then we're fine. Like literally, there's no constraints. Maybe I'm not writing this. Let's think for 8, 1, 2, 4, 3, 6, 5. 8, 1, 2, 4, 3, 6, 7, 5. How I would do it. 8, 1, 2, 4, 3, 6, 7, 5. So first, whatever's in 8, let's say step 1, in the beginning, there's some x in 8. This is x, right? This, no constraint. This will just become x. No, okay. Be x, x. This is step 1. Step 2, it's fine. This becomes x, x. 2, 3, 4, 5, 6. Step 3, this becomes x, 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 something, something, something. So far, no constraints at all. No constraints. X. Now, step 4 is the problem because it's equal to whatever's in 3. So that's the first constraint. So that's the first constraint. If this is x, then maybe I write x. This becomes, okay, after step 1, this becomes x. After step 2, this becomes x. After step 3, becomes x. After step 4, this will become whatever is here. So this has to be x. So then I have x, 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 x. X. Then step 5, 2, 3, that's fine. Step 6, 1, 2, 3, 4, 5, 6. This has to be x. This is the next constraint. This is x. Step 7, this is x. X. I see. So now the total possibilities you have is this x can be anything, right? And 4 of them are stuck there. So you have, let's say, m times the other 8, the other 4, I can think, yeah. 2, 3, 4. M times m to the 4. So that's m to the 5. I feel like I'm doing something wrong. Oh, sorry. 54. 54. So 54 to the power 5. 54 to the power 5 10 to the 9 plus 7, mod 10 to the 9 plus 7. Okay, so I will just check whether this number is equal to that. Oh yeah, I need hmm, what it's called. Oh yeah. Yeah, I definitely will need binary power. Thank goodness for binary exponentiation, man. Okay. Does this do mod more? Oh, this expects that I have. Oh, that's why I had to get the whole package. I see, I see. Okay, so my templates were fine. Slash templates slash. Oh, okay, not there. Let's do it here. Mod. Yeah, is the mod 10 power 9 plus 7. Layout binary power. I wanted to check 54 per 5. 54 comma 5. Oh, 459165024. 4591650. Okay, that looks about right. Okay. Okay, now I need to worry about if there is already an element there. How does that change things for me? Okay. Um, okay, I like the progress so far. That's been good. If there is an element, what happens? Hmm. Okay, let's go over the same problem and assume there's an element. How will that affect the constraints? The ones that can be whatever. So there are like free guys that will end up being the correct value no matter what. So if there's an element here, then don't multiply m, right? That's what happens. If it's free, okay, so I'm defining, I would call, so I would call even 5 free here. So I would call this free. So free means irrespective of what it is, it'll work out. That's fine. So, oh no, I can't call 5 free actually. Uh, okay, let's call it free for now. Let's see what how. So free, okay. So if it is a free index, um, oh, this sounds like physics. If it's a free index, then if it's 0, multiply by m, else don't multiply. That's it. If it's restricted, no, yeah, if it's not non-free, if it's 0, don't multiply because it will have to be a certain value. We don't know what it is at the moment, but it will have to be. Else, you need to check. Hmm. Okay, I would call it free if, okay, let me call them free to pick and not free to pick, okay? Can't pick. This is a can't pick index and this is a pick index. Index. If it's can't pick index 0, that's cool. Multiply by m. Else don't multiply. Right? It's a pick index. If it's 0, don't multiply. else pick index okay, this if these are all 0, multiply by 1m. Any non-zero, check that they are all equal, and equal. Yes, whatever return previous answer. No, return 0. Oh shit. Yeah, return 0. Yeah, this algorithm looks good to me actually. So you start with 1. Okay, so all you do is go over the array, assigning indices as free to pick and not free to pick. And for all those that are free to pick, that are not free to pick, if you see a 0 there, multiply by m. Otherwise, just don't multiply. You can't do anything. For the ones that you're free to pick, if they are all 0, then you get to multiply by 1m. But if any of them are non-zero, check that they're all equal. If it's yes, return the previous answer. If it's no, return 0. Okay. This makes sense. Let's go over it for 0202. 0202. Okay. First, we don't even look at the array. We just look at the permutation 2143. Okay. And we are assigning indices as free or to pick. P is you get to pick, D is you get to not pick. So let's say D and P. Okay, this is a D. This is a D. This is a P. I get to pick, and this is a D. So basically, if Pi is less than I, then you assign it as D, else P. But except for one, if Pi not equal to I guess, then it's D. Else if P1, yeah. Actually, I'll test this with some lead PD. Okay, awesome. Now for the ones that are D, okay, now I put my array. 0202. Okay. Now if it's a D and it's 0, I multiply by m, right? So m else don't multiply. So here I don't do anything. Then all 0 multiplied by 1m, all non-zero, check that they are equal. Oh, this is wrong. Can't do it like this. The only ones that you literally can pick are the ones that are not equal to something else. Sorry, are the ones that are equal to itself, right? Everything else is fixed. Okay. Ah, this is confusing. Okay, I think the video is going to be quite long. It is quite long, and I will take some more time to do this. So I'm going to stop here. But yeah, this is a fun problem.